Hello and welcome to another video on learning APL with neural networks. In this video we are going to be talking about the rank of an array and about the rank operator. So if you are familiar with these two concepts, feel free to skip this video, otherwise just sit tight. Okay, so the rank of an array, we can actually start by giving the formal definition, and then we'll try to understand what it means more intuitively. So the rank of an array is the length of its shape. So a matrix has shape given by its number of rows and its number of columns, and this shape has length 2, and so the rank of a matrix is 2. And the length of a matrix, the length of the shape can be obtained like this, right? It's the tally of the shape. So we can actually see it becomes green, so you can see the color changing because this is an APL looks at these two tokens, and instead of doing the shape and then the length, it just outright computes the rank of the array on the right. So the rank of a vector, can you guess what it is? It's 1, because a vector has shape equal to a one element vector, and so when you ask for the length of the shape you get 1, and a scalar has rank 0 because the shape of a scalar is the empty vector and therefore its length is 0. And we can go the other way around, so we can increase the rank of things. For example, this array right here, this array has rank 3. Sorry, I meant to do that, the length of the shape. It happened that it was the same, but yeah. And so the rank, you can think of the rank intuitively as, or not intuitively, it really is the number of dimensions that a given array has. So a vector only has one dimension, and visually speaking it's horizontal, kind of, yeah, so it's single dimension. A matrix has 2 dimensions. It can go across the screen and from the top to the bottom, and then higher dimensional arrays, they become harder to visualize, but for example we can think of these planes right here as being maybe stacked on top of each other, so this is one of the dimensions, it's that stacking, and then 2 additional dimensions from the matrices themselves. So yeah, this is the rank of an array, and you compute it with the tally of the shape. Now, why is this relevant? Well, because there's this interesting primitive that we want to use, and that helps us do some operations in useful ways. Let's say I have this matrix, let me call it mat for matrix, and let it be maybe 4 by 5, reshape. Yeah. Okay, so this is the matrix I have. This is a numeric matrix, and now say that I want to add to each row a specific number. For example, say that I want to add 3 to the first row, and 5 to the second row, and 2 to the third row, and I don't know, 10 to the last row, for example. It doesn't really matter. Say that I want to do this. How do I do that? What's the code that I should write in order for this to work? Well, I can't do mat plus this because we get a rank error. It says that the left and right arguments have mismatched ranks. In other words, APL doesn't know how to add a matrix with a vector. So what we need to do is we need to tell APL that each scalar on the right should be paired with each row on the left. That's what we want. And will that work? Or would that work? Yes, it would, because if I take a vector and if I take a scalar, this addition works. APL knows how to compute this. And so that's essentially what I need to do. I need to pair these scalars on the right with the rows on the left. And notice that I said that the rows on the left, we can look at them as being vectors. So this is useful. You can look at so there's scalars, and the rank of a scalar is 0. Now, vectors, you can think of them as a series of scalars strung together, obviously. And so a vector, which is a rank 1 array, is just a series of scalars. And then you can look at a matrix, which is rank 2, as a series of vectors stacked on top of each other. So a rank 2 array can be seen as a collection of rank 1 arrays, and you can keep going. This rank 3 array, this can be seen as 3 rank 2 matrices put together. Well, if it's a matrix, it's obviously rank 2, but this rank 3 array can be seen as 3 matrices put next to each other. So there's this idea that a thing of rank n plus 1 is a collection of things with rank n. Yeah, and so we wanted to do this pairing. So we want to take the matrix and we want to add these numbers to each of its rows, which are the vectors or the things of rank 1 that are inside the matrix. And so what we do is we use the rank operator to do that pairing. How do you do that? Well, the rank operator is this symbol right here. And notice that this looks like a jot. And the jot is, you can type a jot with APLJ, right? But then this jot over here has something on top of it. It's a diaresis, I think. I think that's the name. Yeah, exactly. So these two dots over there on top are called diaresis. So because it's a jot with a diaresis on top, the way you type it is with APL Shift J. Okay, so this is the rank operator. And now what you need to do is you need to provide a right operand. So the left operand is the function you want to modify, that you want to pair up, or that you want to use when pairing up different things. And now you need to put 2 numbers in here. In general, you need 2 numbers. The number on the left specifies the rank of the things that you want to take on the left. And so because we want to look at the rows, we want to look at the rank 1 subarrays, and then on the right we want to look at the scalars all by themselves. And so we insert a 0 here, because this vector, the things that are rank 0 inside this vector are the scalars themselves. And so when I do this, what happens is that the first row got a plus 3, the second row got a plus 5, and the last row got a plus 10. Okay? Now say that instead of adding a different number to each row, say that we actually wanted to add the following vector. So 10, 100, 1. Yeah. So this is 5 elements long, and so are the rows. So suppose that we wanted to add this to each row. Can we do this like that? No, we can't. Again, matrices and vectors cannot be added. But what we can do is we can use the rank operator, so plus rank, to say that each vector on the left should be mapped or should be paired with the vector on the right. And so it's a 1-1, because we are pairing rank 1 things on the left with rank 1 things on the right. And now this performs the addition that we wanted. And in this particular case, because these 2 operands are the same, you can just insert 1. One of them, I mean, because when there's only one of them, it assumes that we want to use the same rank for both sides. So yeah, this was very quickly the rank operator. If you're struggling a little bit with it, that's perfectly fine. I still struggle with it a lot. What I can recommend is Richard Park's videos on the rank operator. Richard Park did a webinar series on the rank operator, if I'm not mistaken, and I'll definitely link those videos in the description of this video. So yeah, just play around with it, try to get a feel for how it works, and I'll see you in the next video. Bye.